So, earlier we saw that you can handle a simple electron transfer reaction. We can use Fourier series expansion and get the response at fundamental and at higher harmonics. You can also use Taylor series expansion, rearrange it and get an approximation for the Fourier series. You can also use numerical method. All of them should give you the same result as long as we use enough number of terms, as long as we have enough accuracy in the numerical calculations. Now, I want to show you how to calculate the NLEIS response for a two-step reaction with an adsorbed intermediate. I am going to illustrate with the numerical method. So, we are going to take a reaction where metal is going to dissolve into metal plus solution, but it goes via an intermediate stage. We have seen this example before. Okay. Metal goes to metal plus adsorb and then it goes into solution. So, the first reaction rate constant is given by K1, second constant is given by K2. Here also we are assuming that the mass transfer is rapid, we are assuming that the solution resistance is negligible. So, we have written the mass balance equation for this. First step forms theta, the second step consumes theta. So, we will write K1 1 minus theta for the rate of formation, K2 theta for the rate of consumption. So, gamma d theta by dt is given by K1 1 minus theta minus K2 theta. Under steady state condition we will set it to 0 and we will call the theta as theta SS. And the first reaction is a electrochemical reaction, second reaction there is no charge transfer. So, it is just a chemical reaction. So, the current Faraday current can be written as Faraday constant multiplied by the rate of the first reaction, and the rate of the first reaction is K1 1 minus theta. Now, if I calculate the steady state theta value, I can set it to 0, rearrange it. K1 value will be K1 at a particular DC potential and K2 of course is independent of potential. K1 we will write it as K10 exponential of B1 E. So, at DC potential of EDC it is going to be K1 DC. K2 is just constant, we can write it as K20, but it is basically a constant. Now, in the numerical method we are going to mimic the experimental method. That means, we apply a potential, we measure the current or calculate the current and then subject it to either Fourier transform or phase sensitive detection. We are going to go with Fourier transform. So, we measure the current or we record the current in time domain and then convert that into frequency domain. So, here step by step, first step is to generate sinusoidal potential as a function of time, it is pretty straightforward. Second, calculate the current as a function of time, and that is where we need to actually use these equations. Once you calculate the current as a function of time at regular time intervals, it is pretty straightforward to subject it to Fourier transform, get the Fourier series expansion and calculate the impedance or calculate the I at any frequency. So, we will record the phase and magnitude. Of course, we record the DC, it has 0 phase. We record the phase and magnitude at omega, 2 omega and so on. So, the first part is generate the sinusoidal potential ES EDC plus ESC 0 sin omega t. To calculate the current as a function of time, we first need to calculate theta as a function of time. When we apply sinusoidal potential at some frequency, the surface coverage, fractional surface coverage will also change or it will oscillate. So, we need to calculate that, and in order to calculate that we need to use the mass balance equation. So, we split it as calculate the rate constant. In order to calculate the current as a function of time, I need to calculate the rate constant as a function of time, I need to calculate theta as a function of time. This is again pretty straightforward. To do this, I need to integrate the mass balance equation. Once I have k as a function of time and theta as a function of time, it is pretty straightforward to calculate the Faraday current as a function of time. Now, K1 as a function of time is easy to write, K10 e power B1 EDC e power B1 EAC. The mass balance equation we can rearrange it and write it as with brackets d theta by dt as 1 by gamma K1 1 minus theta minus K2 theta. K1 of course, we have to expand it and write it as K1 DC e power B1 EAC. This is a first order linear ordinary differential equation. As far as I know, there is no analytical solution for this. For a given initial condition, it does have a unique solution, it is guaranteed to have a solution and it is unique, but I am not aware of an analytical solution for this. We can do numerical integration anyway and get theta as a function of time. So, we assume we apply a DC potential and at certain time where we say this is time t equal to 0, we will start applying an AC potential. So, at that time, just at that time or until that time, the theta value is theta steady state, which is calculated here. So, we will write at time equal to 0, theta is theta steady state, and after that we apply sinusoidal potential and we can calculate the response. So, just a description of the Matlab code that we used. K10 it is 10 power minus 9, B1 value is given here, K20 gamma value at certain DC potential and AC perturbation 0.1 volt here means 100 millivolt, and for one frequency we can use certain number of cycles. We do not want to apply one sinusoidal potential and look at the response. We want to apply many sinusoidal potentials and look at the response. There is a reason for that, we will see when we see the results. Okay. And within one cycle I have to collect data at many points. We will use 32 points, you want to use 2 power n, so that Fourier transform is easy to do. And the period of one wave is of course inverse of the frequency, and I can calculate the time interval based on that period and the number of samples we want to take in a cycle. And you can generate a time vector saying starting at 0 at these intervals go for so many cycles or go for this much time. And to calculate the steady state value, we can calculate the K1 at DC, K2 of course is independent of potential. You can calculate the steady state theta value and use that as initial value. And we want to use this equation d theta by dt and integrate. So, we use a certain set of parameters, are given to the program. We need K10, B1, K20, gamma, DC value, AC value and the frequency. Of course, omega is 2 pi f. Okay. Now, by default, if I remember it, Matlab uses a tolerance value of 1e minus 6, that is 10 power minus 6. If you want to get accurate results, you can change the tolerance value. And here we have used ODE 45 as the numerical solver. We use what is called anonymous function and we create a function called d theta and we pass the parameters to that. T vector is basically going from 0 to so much time with this initial value and with this tolerance values. The function d theta essentially takes these parameters K10, B1, K20 and so on, and this is dy here represents d theta by dt. We first generate EAC as EAC 0 sin 2 pi f t or sin omega t, and potential is EDC plus EAC. K1 is of course K10 exponential of B1 multiplied by potential, and K2 is K20, and d theta by dt is 1 by gamma multiplied by within brackets K1. So, this entire term I can write it as K1 1 minus theta K2 multiplied by theta. So, if I do this integration, what do I get? For certain values K10 is 10 power minus 7 moles per centimeter per second, B1 is 15 inverse of voltage, K20 a certain value gamma with 10 power minus 7 moles per centimeter square, and a DC potential of 0.5 volts with respect to open circuit potential. When we are away from open circuit potential, significantly far away from the open circuit potential, we can neglect the reverse reaction. And we have done it for a few frequencies. Here I am showing you the result for 1 kilohertz and 100 millivolts. Later we will see the results for other combinations of perturbation amplitude and frequencies. First thing I want you to notice is the following. When we apply a AC potential, the response is not immediately a steady periodic response. This theta value increases and then stabilizes after some time. Okay. We have seen this before. When initially we looked at an RC circuit, if I just take the Fourier domain and calculate the resistance here, use the resistance here, use the resistance here and use the capacitance here, I can find the impedance. But if I supply a sinusoidal potential, it will take some time before it gives me the steady periodic result, and if I take the steady periodic result and use Fourier transform, I will get the same expression for impedance. If I take the response in the beginning before it stabilizes, I will actually not get the impedance that you would get by adding this as R1 plus 1 by R2 plus j omega C2. This is the expression we get when we use Fourier domain or frequency domain. So, out here by using numerical method, when you integrate, you realize that it will come to steady periodic result only after some time. It takes some time to stabilize. In the beginning, it starts at close to 0.8. The fractional surface coverage was close to 0.8. It increases and it oscillates around a value which is probably close to 0.91 or 915. If you just read off the graph, you can see that after some time, when we are close to 0.09 to 0.1 second, that is close to 100 milliseconds, it has stabilized. So, this inset shows the result close to this value and this inset shows the result close to this value. So, it takes some time to stabilize and give steady periodic result. Second point is it does not oscillate around the initial value, it oscillates around a different DC bias. So, the summary is the response is not steady periodic in the beginning. The average value of theta after stabilization is different from the steady state value. If I just apply DC potential, I will get a steady surface coverage value. If I apply AC on top of this, average potential is still EDC, but the average surface coverage is not theta SS. And how long does it take to stabilize? What will be the average surface coverage when it is oscillating, when it is under steady periodic condition? This will vary with the applied perturbation, amplitude of the perturbation, it will vary with the frequency. We will do that analysis later. Right now, we will say we will wait for sufficient time to get steady periodic response, and after that we will subject this to Fourier transform. So, we will record the data after stabilization, record or save the data. We will calculate the current at least for one cycle, it is probably better to do it for many more cycles, okay, and then subject the current to Fourier transform. Once you subject the current to Fourier transform, you will get a Fourier series, constant coefficient, coefficient corresponding to sin omega t and a phase, magnitude and phase for a sin omega t, magnitude and phase for 2 omega, magnitude and phase for 3 omega and so on. If I want to calculate the impedance, I can calculate the magnitude of the impedance by taking EAC 0 and the magnitude at 1 that corresponds to omega. If I want to calculate the phase, phase is 0 for the potential, phase whatever we calculate or get for the current, we can subtract that and get the phase of the impedance. And once you do it for one frequency, you can do it for other frequencies and then generate the spectrum. So, in order to implement it, we can give the parameter values. Previously we have seen how to calculate the theta. In order to implement it correctly, we have to wait for some time. So, we have to say wait for, in this case I would say wait for 100 millisecond or wait for 0.1 second and then take results, or at least wait for 0.05 seconds and then take the cycles. So, in order to do it correctly, it is good to wait till a complete cycle is done. So, we calculate the number of cycles that one needs to wait, so that the response has stabilized, and then we have to integrate it, and whatever value of theta where it ends, that should be the initial value for the subsequent integration. That is, you apply sinusoidal potential, wait for some time and then take the data. So, the theta value and the current value should be at that end. So, we calculate the theta values and then the last value of that theta should be the initial value for the next integration. So, until now we have been waiting, now we are going to record the data. So, this num cycles tells how many cycles we want to use to record this. So, at certain time interval you can do the integration, and once you get the theta values, you can calculate the rate constant, you can calculate the current using this expression, and then you will remember that if I give a sine wave like this, I of course give discrete points here. For this implementation in the Matlab, I should not give all the way until this, I should actually give 1 point less. So, I can give up to this, and then Matlab will assume that we are going to replicate it and then do this Fourier transform. So, I find the length of this current and then give 1 point less. If I want to look at the response at fundamental, I should look at the second term in the series. If I want to look at the response at second harmonic, I should look at the third term, because in Matlab first term corresponds to the DC, second term corresponds to omega, third term corresponds to 2 omega, and so on, if you are using one cycle. If we use many cycles, the Fourier transform will give you response like this: 0, let us say we use 10 cycles, 0.1 frequency, 0.2 frequency and so on, and then 1 frequency, 1.1 frequency and so on. Because the more number of cycles we give, the better resolution, meaning instead of going from 0 to 1 in one step, it will go in 10 steps or n steps. A number of cycle will give you n steps. So, correspondingly we should look at the right coefficient based on number of cycles and then take the value for the first harmonic. And because of the way it works, you have to multiply by 2 to get the magnitude, you have to add pi by 2 to the phase. Now, we get the current, magnitude and phase, and to calculate the magnitude of the impedance, EAC 0 by IAC 0 will give you the magnitude of the impedance. Phase of the impedance is basically 0 minus the phase of the current, and the nonlinear impedance ZF nonlinear is nothing but Z e power j phi, where phi is the phase of the impedance and magnitude of course is mod Z. As an example, if I give 20 millivolt at 1 kilohertz, few time intervals here, right, 1 millisecond I would get 1 cycle, few time intervals I got some numbers. Correspondingly, DC potential of 0.2 plus 20 millivolt sinusoidal will give me a value like this. After waiting for sufficient time, when we continue with the integration, these are the theta values, and correspondingly I will get current value. Of course, I have truncated, it would give many more decimals, I have truncated it so that we can see it easily. These numbers are not identical, 0.8 and 0.8, these are actually slightly different, but you get the idea. Now, take this current and the time interval, this is the sampling interval, and subject it to Fourier transform. Once I subject it to Fourier transform, I will get results like 0, f, 2f and so on. This is the raw value, it is a DC, this is a complex number, this is also complex number, this is also complex number. After 4f it is going to be 0. Here I have used only one cycle, therefore, after the first DC bias, next term is the response at fundamental. I had to multiply the magnitude by 2 and add pi by 2. What I also want you to note is even though I am applying 20 millivolts, it is actually fairly small perturbation. There is some response, a small value at second F. There is even a smaller value, but not 0 value at the third frequency. Only for fourth and fifth harmonic, we see it is pretty much 0. And if we do it for a set of frequencies, we can get the results and plot it in complex plane plot. 1 millivolt and 20 millivolts, you get two semicircles for a set of kinetic parameters. 1 millivolt is given as a dashed line, 20 millivolts given as a circle, and you can see they pretty much overlap. They show two semicircles. This is the value at low frequency, and this is just an expanded version at the high frequency and mid frequencies. The response at 100 millivolts is given by the green color square. Response at 150 millivolts is given by blue triangles. I want you to see this. This will correspond to charge transfer resistance, and this values correspond to polarization resistance. When I increase the AC potential, this is going to settle somewhere here. So, 1 millivolt to 20 millivolt, there is not much of a difference. 20 to 50, the nonlinear charge transfer resistance increases. So, at 20 to 100 it increases, 100 to 150 again increases. So, RT NL increases with AC 0 for this case. Earlier example where we have looked at simple electron transfer reaction, when we increased the perturbation amplitude, RT actually decreased, but that is not universal. RT can increase, it may increase or it may decrease. Next, I want to look at polarization, nonlinear polarization resistance, that is the low frequency value. 1 and 20 millivolts, it is pretty much the same. 20 to 100 it decreases, 100 to 150 it actually increases. That means, if I plot RPNL with 1, 20, 100, 150, not necessarily drawn to scale, it is constant, it shows an decrease here and then an increase here. We do not know whether it is a minimum here, it is just to say it is not monotonic. So, to summarize, for this reaction, two step reaction with adsorbed intermediate, we have to take the mass balance equation and the current equation. We do not have to expand this in Taylor series or Fourier series, just integrate the mass balance equation. First find the steady state values, use that as the initial point and use numerical integration, take the mass balance equation and integrate it. So, generate sinusoidal potential, solve mass balance equation using a ODE solver. We have used Matlab and ODE 45 or ODE 15S. You can use any similar software, you should be able to do the integration. Recognize that it takes some time for the response to stabilize, wait for certain time and then start recording the data, and this is true even when you do experiments, okay, because the system takes certain time to stabilize. Once you have waited for sufficient time and start recording the data, save the current data as a function of time, subject that to Fourier transform and record the values at DC, record the response at fundamental, response at higher harmonics, both the magnitude and phase, and then you can calculate the impedance. You can plot the current response at any harmonic as a function of frequency in Bode plots. So, we saw that it takes some time to stabilize. What we would do in the next class is to look at the effect of changing perturbation amplitude, look at the effect of changing frequency, and then get an idea of how these things affect stabilization time, how these parameters affect the average value or mean value around which this stabilizes. After that, I also want to discuss how to estimate the charge transfer resistance and the polarization resistance for any perturbation amplitude. For small perturbation amplitude, we know we can linearize the equation and get an expression for RP and RT, in fact for the entire impedance spectrum. For large amplitude perturbation, it is not possible to get an analytical expression for any reaction in general, but for many of these cases we should be able to estimate the charge transfer resistance, and we will be able to calculate the polarization resistance without going through the integration. Okay. We will stop here today.